Around 2001, I met a brother of a friend, and he just finished his bachelor's degree in computer science, and I asked him, well, what are you going to do now? And he said, oh, I'm starting to work in some startup that's putting a camera on vehicles and doing all sorts of machine vision algorithms. And I asked him, well, what are you going to do with that? So he said, well, the long-term goal is to have the car drive by itself. And I thought to myself, here's another pretentious startup that's going to fail. And about 7 years later, when I got to a stage where I wanted to find a work in a high-tech company, that same person convinced me to come and work with them. And that's what I've been doing since, trying to make this dream come true. So I want to tell you about that. Okay, so the truth is that demos of such systems, of cars that are driving by themselves, were done even in the 90s. Various universities and car manufacturers had all sorts of demonstrations of the technology. And the question is, well, what's really the gap between just having a demo and making it into a product? So you will go into the car dealer and will order a car that is able to drive drive by itself. So there's three main hurdles to making it into a product that we need to think about. The first one is the price. So in most of the demo systems that have been shown, the equipment that is on these cars costs hundreds of thousands of dollars. And to make it a product, we wanted to reach the order of magnitude of $1,000. The second hurdle is that we need to integrate this into the car. So, for example, the Google car that's been shown several years ago has this nice Velodyne laser scanner on top of it. That's something that no car designer would allow you to put on a car. There's all sorts of issues besides design which you need to integrate into that. So, for example, many of these demo cars, their trunk is just full of equipment. Where would you put your the things that you bought? So that's the second issue. And the third issue is that you want to make it work everywhere. A lot of these demos are fine-tuned to a particular path that has been, that the team has been working on to make it work in that path. But you want to make it work everywhere in all kinds of conditions to make it into a product. There are, by the way, also a different strategy which says actually you don't have to make it everywhere. There's people talking these days about taking several central cities, closing down certain districts, and having autonomous taxis drive in these parts of the city. Perhaps you won't be able to even to drive with a regular car. It would be only the autonomous taxis. So that's a particular case where maybe it's enough to just make it work in a limited region. But the thing I'm going to talk about today is really that you can order the car wherever you live and have it drive for you. Okay, so these are the hurdles, and the question is really what I want to tell you is how do we see the process of getting to pass all these hurdles? And the story that I'll try to sell to you is that it's a very incremental process. It's not a big one, just one big jump. And it's in fact a process that has been going on for a while. So starting around the early 2000s, many different car manufacturers have started to put in their vehicles systems which are called driver assistance systems. And what I want to show you is how the abilities of these systems is incrementally increasing every year and on a path that eventually will take us to autonomous driving. How does Mobileye, the place I work at, fit in with that process? So that's our major business. So Mobileye, I think for most people is known, at least in Israel, is known by many by the aftermarket product, which you hear commercials that you can put on your car. But really the main business is that we work with car manufacturers to put our camera built into a new car as part of a driver assistance system. So I want to show you what these systems are doing in the past few years. So if we go only 6 years ago, 2010, we came out with General Motors. So General Motors came out with us, would be more exact, with a system which gives the driver alerts if there's a danger of collision. So that's their...
That display will flash and you'll get a series of high-pitched beeps.
Okay, so that's the demo of that. You can't actually see very well that it's a dangerous collision, but it's the same abilities that we have in our aftermarket system, just giving alerts. So that's how these things started, and that's what these systems did initially. But at that same year, another system came out with Volvo, which is much more risky, you might say. And Volvo actually used our camera to do emergency braking. So our camera, as I will show you later, can detect pedestrians. And Volvo decided that they're going to do, if our camera detects a pedestrian, which is in immediate danger of being driven over, then the car would by itself exert a hard brake. And what I'm going to show you here is an experiment in their test track where they test whether that system works. So you see this doll here of the child that is running to the street. And this braking that you've seen was an automatic braking. And so this system already came out, and that was a fairly courageous move on Volvo's behalf to actually trust the camera enough to do this kind of thing. So the car brakes for the driver. In 2012, another system came out, less risky but still useful. And here, Volvo used our camera that recognizes signs to recognize that there's a speed limit in the road that you're driving at right now. And the reason this was commercially attractive is that in certain roads in Europe, if you actually pass the speed limit by not too much, you might get a really high fine. So they really like that feature. Here's a feature that I really like. So this is again with Volvo. They have these, in some of their cars, they have the headlights have the ability to change the structure of the what's it called? Aluma. The beam. Yeah. So what we do is we join the two technologies, our technology to recognize the car and their technology to change the shape of the ray such that the vehicle in front will not be blinded, but everything around it would be in the light. So it looks like that. And the effect is that when you're driving, you feel like you're in the high beam mode, whereas the car that's coming across thinks that you're in the low beam mode because it's not being blinded. And actually, there's in the aftermarket that we sell, also here in Israel, I have it in my car, you have a more primitive thing which is like that, which is just it changes the high-low beam for you with regular headlights. But this is really a much nicer and more elegant solution. Okay, so here the car plays with the lights for you. Now here's really initial signs of autonomous driving. In 2013, BMW used our camera to drive the car in a traffic jam. So that's really autonomous driving in a very, very simple setting. So the car turns the wheel and applies the brakes or the gas pedal by itself. And it's guided by the lanes that we detect and by the vehicle in front that it detects. So that's a fairly simple system that already shows initial signs of driving by itself. Now, around that time, it was kind of clear that the whole car industry is going to the direction for autonomous driving, and that car manufacturers are starting to want to make bigger jumps towards vehicles that can drive themselves. And in Mobileye, we decided in order to make our camera better for that purpose, to have our own autonomous vehicle in-house. So we purchased an Audi vehicle that you can control from a computer. You can control the steering wheel, you can control the gas and the brakes. And we've built a team that started to build a controller. Okay, so the camera recognizes different things in the road. I'll show you in a minute. The controller analyzes, decides how to control the vehicle, and the car drives. And in 2014, we already had a prototype of this Audi vehicle that's driving by itself. I want to show you how it looks like. So it's this Audi on the left. And now currently it's driving by itself. You see it driving on the road from Jerusalem to the Dead Sea, if someone recognizes that. Now here on the left, you see what our camera sees. Okay, it's this black and white image, and you see overlaid the things that the computer vision algorithms detect. So you see these green lines which detect the lane. Oh, sorry. You see the green lines of the lane detection. You see the detection of the vehicles, and that's what the vehicle knows about its environment. And then there's the control system which decides how to steer the wheel. You can see the driver here is not putting his hands on the wheel, his legs are not on the pedals, and the car is driving by itself. So let's see a little bit how it looks like. Okay, so this is more or less what it knew how to do, at least 2 years ago. It's a 2-year-old movie. Today, actually, it also changes lanes. I actually went to a drive a few weeks ago, and it's funny because it tells you when it intends to make a lane change. Today, it also has other cameras which see the side, so it knows actually if the next lane is free or not. And you see that it intends to make a lane change, but it's not doing it yet. And then, when it's clear, it makes the lane change all by itself, and then later goes back to the original lane. And we found ourselves when we talk about it, what it's doing, that it's actually hard not to talk about it in humanistic terms. It wants to make a lane change and things like that.
What makes it want to do change?
So it's of course not something very sophisticated. You set a speed, and it drives on the right, but then there's a car in front which making it drive too slow, so it just switches to the left lane, speeds up, later returns to the right lane. It's fairly simple logic. Okay. Yeah?
What decides its location in the lane? You know what I'm saying?
It's in this at least mode, when it just want to stays on the same lane, it's trying to center it at the lane center. Yeah. There are, of course, cases where I didn't show here because I don't want to waste too much time on the movie, but later there's something on the side, so it decides to veer a little to the left to keep a safe distance. So it has some also abilities of that sort. Okay, but the exciting thing which happened, sorry, another question? Yeah. So actually, the system that we have currently has. The question was why don't we also look back? So the truth is that our current vehicle has 8 cameras which give a 360 degrees field of view. So it also looks back, and it gives you the entire thing around. But I won't show that today. I'll just show front camera things. Okay, yeah.
Why are you using the cameras rather than the laser? Measure distance.
I'll talk about different sensors in a second. Our expertise is on the camera, and that's our product. Car manufacturers use a bunch of sensors, and I want to show now the Tesla example, they use a camera and radars. That's usually the combination. Later we'll talk a little bit more about that. But I want to show really the exciting thing which happened last year is that for the first time a product came out which is autonomous driving to some extent. And we've been working with a number of car manufacturers, and Tesla have been the first one to come out with this feature.
I'm not touching it. No, the car's watching. It sees. Oh my gosh, the car knows exactly where the person ahead of me is in the lane. Because I can see it here on the dash. And red light. But that was.
To me, it's actually I'm using to see the reactions to the product. The first time that I drove our autonomous car, and I also drove some car manufacturers' prototypes. That is the reaction, because you're really afraid. You feel out of control. The car is doing things by yourself, and you're just like that on the wheel, waiting for something to happen, and you'll catch it. But after a while, you adapt, and you realize that actually, even if your hands are not like that, you are fast enough to react, and you start to trust the system more. Yeah.
It says for highways, but this is not a highway. So
yeah. So it was designed for highways, and the goal was to make it work well on highways. But people are using it everywhere, and it sometimes works on other roads as well.
will it not engage if there's a situation where it wouldn't be appropriate? I mean, what if a person walks on the street here? Does it have detection of?
Yeah, it detects people and different obstacles. We'll talk more about that.
Weather is bad, and what if it's dark? What if there's fog? I mean,
It has these. I think it happens later in the movie where it says it thinks it's not sure enough about what's going on, and it turns itself off and gives this beep that you need to take control.
because if it's not fully perfected, I can see a lot of risk coming from this. So I'm just curious how you deal with that.
So it's not really directly us, but the car manufacturers, they say the full responsibility is on the driver. He needs to keep an eye and be ready to intervene if necessary. It's a convenience, so it's your responsibility.
Okay, got it.
And
I think that's why they've changed the name most manufacturers from autonomous driving to semi-autonomous driving, so the responsibility will always be on the driver to identify risk, right?
maybe, I don't know. I'm not sure about the name. Maybe, could be. Yeah. Okay, so so this is where we are today. This is the state of the art, and what I want to talk about now is a bit more about the engineering of these systems. So how do we build it? Okay, so if you would sit down and think, if you want to build an autonomous car, you would think about the requirements that it needs to obey. You'd probably come up with three main things. One is you want it to get to where you want to get to. The other is that you don't want to make accidents on the way. And the third one would be that you also don't want to break any laws. Okay, that's basically the things. Now, to be able to do these three things, you need various information from the environment. One piece of information that you need is to know at each instant what are the drivable lanes that there are right in front of you. Okay, so you would know where to steer to. Now, naively, you might think that this problem is already solved, because we all know that cars have navigation systems, and they have a map inside with the structure of the roads, and they also you have a GPS which localizes you in the map. So naively, you might think we could already use that to drive a car. The truth is that that information is not accurate enough. So in the information that you currently have in the regular systems, you have accuracy of around 10 meters in localization, or the accuracy of the maps. And to drive a car, you need accuracy of 10 centimeters or less. That's what's our experience. So there's a gap, a technological gap in there. As for accidents, you would want to be able to detect all sorts of obstacles that might occur, or to know what is the space which is safe to drive in at any instant. And in order to drive in a lawful way, you would like to be able to recognize all the different information that's out there for drivers. Okay, so what technologies do we have to extract these types of information? There's different types of technologies. One type of technology is could be communication between vehicles and infrastructure that you have there. You could have the traffic lights directly communicate with the cars, or you could have cars communicate with each other. These are things that people are working on. The main limitation is that it actually becomes effective when it's really spread out. So when a lot of cars have these communications, or a lot of the infrastructure out there has this communication ability, then it becomes really an important contribution. But we're not there yet. So you need also other types of information sources.
What about the cell phone towers?
About what?
Cell phone towers.
What's that?
Cell phone. The cell phone.
Cell phone. Oh, yeah, that's an idea that's out there too. So if you know that there's a cell phone moving here, there's probably a pedestrian crossing the street, and things like that. Is that the kind of or the cars themselves?
The cell phone towers.
Oh, the towers.
Compared to the
Right. That's another kind of infrastructure that you could use. Yeah, I don't know much about it in terms of what's the technological gap that remains there in terms of accuracy, but it's certainly a direction. Another direction is to use map databases. So a lot of things in the environment are fairly constant, and you can map them to begin with. There's a challenge that we said before that has to be accurate enough. And the main limitation here is that there are things that do change, so you won't be able with a database to predict that the child is going to run into the street. So it's not the whole story, but it's definitely part of the story. I'll talk a little bit about that. And then the third direction is to use sensors, which just give you information on what's currently going on outside of your vehicle. Different sensors that we have are the leader, which is has this this thing which has a bunch of lasers which are scanning the environment. You measure the reflected light, and by the time of flight you can know the depth. So if you scan around, you can get a 3D reconstruction of the environment, which is very important information for the things that we mentioned before. This is a video from Google where they use this scanner to get the 3D environment around them. It's a very, very powerful sensor. The main limitation today is it's, one at least, is the price. It's still tens of thousands of dollars. And there's also the issue of integrating this thing into a vehicle. So far in the vehicle industry, I saw relatively little use of leaders, but it might change in the next few years maybe. Then there's the radar, which is a good way of measuring metallic objects in your area. So you transmit waves, electromagnetic waves. You measure what's reflected. And that radar has been used in the car industry for a very long time. They're fairly cheap, and they're very useful. And most of the cars that do the different sort of things that I've shown you use also radars. And then finally, there's the camera, which is our expertise. So this is actually the way our camera looks like, at least encased in its the way what you attach to the windshield. And the camera is a fairly natural sensor for doing autonomous driving, because all the roads and the signs and everything is designed for the visual system of the human driver. So the information is out there. The camera can see it, but the challenge really is the algorithmic challenge. How do you actually extract it from the image? And I'll talk about that in several minutes. But before that, I want to mention another challenge. So we said that we have different pieces of information that we need to extract from the environment in order to drive a car. But that's actually not enough, because suppose you know everything you want to know about the environment, there's still the issue of planning. So if you consider, for example, this scenario, suppose you use this car, you want to get out of the traffic circle. If you'll do it right away, you might crash into this car. So it requires planning. You might want to slow down, let that car pass, and then perhaps drive out of the circle. And you meet many of those planning problems when you try to drive a car. When you think of it, when you take driving lessons, the issue there really is not the motor control or learning to recognize traffic lights. You're able to do that from the start. Really, one of the main things that you're actually learning as a human being is you're learning how to behave inside this complex environment, for example, like driving in Tel Aviv. So we have also the challenge of how to make an automated system that would be able to solve these problems. So I'll talk a little bit about that too. Okay, so our business really is the camera, and we try to do as much of all these things with the camera, and I want to tell you about that. Here you see the camera, and this is a picture of the chip. So it's not just a camera, it's a camera with a brain. This is a chip that was designed by us, and it runs algorithms that we developed. Okay, so when we sell car manufacturers the camera, we sell it, of course, with the chip, with the software. Okay, so I want to show you some of the things that our algorithms are able to do, problems that they solve that are relevant for the autonomous driving. So one problem we said was to know the lane structure at every instant. And one algorithm that we have in our system is a lane detection algorithm. I'm actually emotionally attached to it because one of my jobs was I was in charge of the team that was supposed to develop this algorithm. And here you see those two lines that detect the left and the right lane marks. And these are, of course, you need them at each instant to guide the steering when you want to drive the system. And this is an example of, I picked on purpose an example where the weather is not so nice and the visibility is not so good to show you a more challenging case. And it's not perfect. Sometimes it has little errors, but it manages most of the time. It functions fairly well. Okay, so this is an example of lane detection. We also said that we need to detect obstacles. In this video, what I'm showing you is a different set of algorithms which detect cars and pedestrians, which are the main obstacles that you encounter on the roads. And around each car or pedestrian which it detects, you see this rectangle, which shows that it's been detected.
What's the difference between the green and the red?
I actually haven't noticed it. Let's see if I can tell you.
It's moving.
It has a text here of which cars it thinks are moving and which are not, but I'm not sure that the red and green are. I think the red one is the only one which is right in front of your lane, but I didn't see too many examples, so I might be overfitting here. Okay. So that's an example of vehicle detection and pedestrian detection. And another information we said that we need is to recognize the signs that are out there. So this is an example of a different set of algorithms whose job is to recognize signs. And here it tells you what kind of sign it detected. So in a short code name. So this is warning, curve right, for example. Let's wait for another sign. Oops, I missed it.
Did this sign affect in any way the behavior of the camera? If you know that there's a sign that says that the road is going to curve to the right, do you change anything in your state?
So in our car today, signs we don't use so much. We use traffic lights. So we want to cross a junction. So if it's red, we know that we need to stop. It recognizes the stop line. It stops next to the stop line, waits for it to be green. When it's green, it continues to drive. Yeah.
Lane detection,
What?
The lane detection, is it mandatory to have the lane marked on the road?
Yes, it is, and that's a problem that we've had. In a minute, I'll show how we try to deal with it. Yeah, right. Because it's only able to detect the lines, and sometimes there are no lines. Yeah, we'll get to that in a minute.
You mentioned the traffic lights,
Yeah.
and it seems that the camera is monochromatic.
Right.
So isn't it beneficial to have it be color camera?
So it's not exactly monochromatic. I mean, the images that I show you are monochromatic. The truth is somewhere in between. So you know that a color camera usually has these filters of red, blue, and green, and that's the way you get the three color channels. Our sensor has on every 4 pixels, it has one of them has a red filter, and the other 3 have no filter. And why do we go for such a sensor? Because the thing is that if you have a color camera, you put these filters, then in a dark night like this one, you get much less photons on your sensors, and it's hard to see in a dark night. So at some point, there was a decision that we're going to do this kind of intermediate thing where we have partial color information, because to have really full color information, you need 3 channels, and we have 2 channels, the red one and we call it the clear one, the one that's unfiltered. And we chose the red filter because the main thing, for example, that we're interested in is to distinguish between a red light, for example, at night, which means a car that's driving in your direction, and a yellow light, which is an oncoming car, or a red and green, and in a traffic light. So it means that for us, for example, it's hard to say if a sign is blue or green, but that rarely is an important problem for driving. So we do have some color information. Yeah. Okay. Yeah.
Can you elaborate on the algorithms you use?
Okay. I'll say not a lot of details, of course, but I'll get into. So the next thing I want. Okay, in the middle, I'll say a few more things, and then if you have more specific questions, then guide me to where you want me to go. Okay. I just want to show, for example, that here it tells you it's a warning, a roundabout, yield, and etc. There's, I don't know if we already crossed 1,000 signs or it's still in the hundreds, but there's many different signs that the system is able to recognize. Okay, so all that I've shown you so far are algorithms from a few years ago. And as you probably heard, I think 2 lectures ago in this meetup, there's a revolution of deep networks. And also in computer vision, it's a very big thing. And in Mobileye, it had a big impact on us. And I want to talk a little bit about that, and also talk a little bit about the algorithms. So as you can imagine, a lot of these algorithms are based on machine learning. So let's pick an example. For example, I showed you a algorithm which detects cars. So how does it do it? So usually, at least a few years ago, the scheme that we usually worked at was you first try to build something that will make an educated guess on where the car might be. And you built a number of hypotheses. It might be, let's say, around here. It might be this piece of the building, maybe a little bit looks like a car, etc. You make these many guesses, and then you use machine learning to be able to answer the question in a fairly strong way whether really this piece of image, is it a car or not? And how do you do that? So what's the framework in machine learning, or at least the way it was then? You take that piece of the image, and first you need to find a set of numbers that characterize what's in there in that patch. We call these features. So for example, it might be in different parts of that piece of the image, what's the directions of the lines? Okay, that tells you something about the shape. Okay, and you use this kind of judgment to think what kind of information in that patch is actually useful to know if there's a car in there or not. And you generate this list of numbers which we call the feature vector. It's these x1 to xn, which you think is a good representation that there's information in there if it's a car or not. Then what you do is you need to get a lot of labeled data. So you need to collect a lot of pieces of images. Some of them will be cars, some of them will be not be cars. You need someone to label these and tell you which are the cars, which are not. And then you build this kind of simple machine that's, the goal is to take a piece, get these numbers, this feature vector, and give a grade. To give a high grade if it really looks like a car, give a low grade if it doesn't look like a car. And this simple machine needs to be something with parameters that you can tune. So for example, a common choice is to take a weighted sum of the feature vector, of the elements of the feature vector. Okay, so these W's would be the weights of these inputs. And then the thing that you want to learn is you want to learn these weights. And then you have learning theory or learning methods on how to change these weights so that on your data set it would give good grade to the cars and bad grades to the non-cars. And then eventually you run it in the system after you've trained it, and it's able to, you have a grade and you put a threshold and you say these are cars and these are not cars. So that was the way we worked before. Now the big revolution now is that instead of using these fairly simple, it's called predictors, these simple predictors, there's much more complex predictors. Actually, they've been around for a long time, as you probably heard from at least the 80s. People have been working a lot with these layered neural networks. But really the surprise was that, that you can actually train them and solve problems. Because before the revolution of the several recent years, the claim was that if you try to actually solve the problem of the cars, let's say, with this kind of network, then it would very quickly converge to some very bad local minima. It will not be actually a good solver. And people at some point started to show that actually it could work. Now, one nice thing about it, because it's much more complex and it can represent much more complex input-output relationships, then the problems that we give it are different from the problems that we used to give. Instead of telling it, well, these are the feature vectors and we've handcrafted them and now work on that, we just give it the original image. So we tell it, this is the image, now you find the car in there. What kind of structure do we usually have in these networks? So here in this diagram you see a typical architecture that's been used in machine vision. You usually do fairly low-level processing and local processing of convolutions. So you might do different convolutions and have different maps. And usually you do it several times, so you get coarser and coarser representations of the image. And then later you do something much general, which does some general input-output relationship and tries to do things which are global on the entire image. And I will show you what you can get with that in a second. So in Mobileye we realized that this is going on and we really have to be ahead of everyone if we want to stay in the competition. And that's in recent years for us really a major tool in solving our problems. So I want to show you some of the solutions that we came up with. Okay, so this is the problem somebody mentioned a while ago, that we had this problem that in some of the roads there are no lane markings. So if you take this residential road, there's no lane markings, but you as a human driver know how to drive. You realize that there's no two lanes, one going this way and the other going that way, although there's no marking, and that you're supposed to drive on the right one. And for us, it was very difficult with the old methods to solve this problem. With lane detection, you can hand engineer something which looks for lines on the road. You could imagine that's fairly simple. But to be able to judge, well, this is a scene, you need to look at the entire scene in a holistic way to know that you need to drive on the right side. So what I'm showing you here is a network that we developed where the input is the entire image, like it usually is with, or a big piece of the image, like it usually is with these networks. And the output that we wanted this network to to give us is to say what is the driving path that you need to go to at different lines in the image. Okay, so it draws the path that you're supposed to drive along. And eventually, we managed to build a network that actually is able, in also these types of scenes that we weren't able to solve before, to tell you which way to drive. So the Tesla that I've shown you before, for example, has this inside. Yeah.
How do you allocate the crowdsourced for that?
Oh, okay. Good question. So in other cases, ground truth is fairly straightforward. So for example, the problem that I've shown you with the cars, you just need people to mark rectangles around cars and over many images, and you're set. But here it's really more tricky. It's hard to give a human being precise instructions on what to mark in here. So what we did here is we have a method, I will talk about it in a few more minutes, of actually computing what is the trajectory of the camera within the world. Okay, so we take this movie, we run it on its entire extent, we compute the trajectory of the car, and we just draw as the labeled data for the network what the car actually did when it drove here. It's not foolproof because the car may have done something which you don't want it to do, but in a very large fraction of the time, it is what you actually want the network to do. Okay, so I want to show you another example of an algorithm that's a neural network. So here the goal was to say what we call what is the free space. So this entire green area is where the network thinks that you're able to drive. Okay, so and the color at the edges tells you what kind of boundary it is. So if it's a red boundary, it means that it's a road edge. If it's a blue boundary, it means that it's a vehicle, the back of the vehicle. They're also pink for the side of the vehicle. And this is a problem that we've been struggling with before with the old methods, which we found was very hard because the way that, for example, a road edge looks like is very variable. To us as human beings, it seems really obvious that here the sidewalk begins. But to actually write in algorithms, even with machine learning, that's able to distinguish between this and just 2 patches of asphalt is not trivial at all. And here with the neural network, we were able to actually make a really big breakthrough.
This continuous lane that you can drive on the other lane? Is it not running through anyone?
Let's see. Oh, sorry.
Was that an error?
I want to get to that. There is a place here where I used to think it's an error, but then I see it's actually right. But let's see if it's that, or of course it has errors. But let's see. Stop me when we get there, or 2 seconds before we get there. This you mean?
Yeah.
No. So there was these bricks on the left, and then they ended, and then it. Yeah. So this was actually right. We still like it to be better than it is here. We want it to be more precise. So there are small errors that we're trying to get rid of.
So in this situation, does it know that the opposite lane should not be driven on?
No, it doesn't know, and we don't ask it to. So we're asking it not what the lane structure is, which is a different question. We're asking it in terms of the 3D physics. Where is it safe? Yeah, where is it flat? Exactly, flat surface.
Do you treat the deep network as the classification problem?
We do, but what I mean, it is. But what do you mean by that?
You can train a network doing segmentation.
So what do you mean by that?
I'm asking if the problem is treated as a segmentation problem or not.
Well, in this case, the problem is treated as we tell the network will tell us at each column in the image where does a free space end? Give us a number. What row does it end? That's the desired output of the network. Does that answer your question? Yeah.
Same question. How do you allocate the contours for that?
How do we?
Allocate contours for that.
Oh, so this is actually manual. Yeah. So we have we outsource it. We have there's a firm in Sri Lanka that does these sorts of things, and there's hundreds of workers that are every day are, several hours a day marking such things for us. Yeah.
Do you use the relative height of the sidewalk, the relative height to the road as a boundary? Or?
What do you mean use we don't know the relative height, so what do you mean by use the relative height?
So most of the sidewalks are higher than the road?
Yeah, but the problem is that we have a two-dimensional image, so
You don't do reconstruction?
we do, and I'll get to that in a minute, but it's a problem in itself. It's not that we, yeah. Other question? Here we don't. Here we just use the image. Only the texture in the image, it's the only information. Yeah. Okay, any other questions? Okay, after the pizza. Okay, let's move. Yeah?
Do you use data from the users to continue training your networks in some way?
Again, data from the...
Like, if you have a camera in a car, does it continue training the network?
Oh, we don't have online learning. Yeah. But we have something in that direction. I'll get to that in a few minutes too. Okay, this is another example of a network that is able to we told it to put boxes around cars. Now, when I say it, it might sound like it's easy, that anyone can, compete with us in the next week. But I want to calm you down that each one of these networks was many months of development and a lot of research, and you're able to get to that, but it's a lot of development effort to actually get to these levels of performance, not just collecting the data, but the development of the network itself. Yeah.
This obviously has some understanding of the geometry of the camera and the road, right?
So I can't get into details, but there's a knowledge expert that we put in terms of things that we know. In this case, in the other cases that I've shown, it's nothing implicit. It's actually it's all image processing, just a fairly sophisticated one. Yeah.
What is the infrastructure that you use? You use GPUs, some kind of high-performance computing, clouds, Python.
In terms of the hardware, we buy GPUs. I won't know to tell you which ones. But in terms of the software, it's a lot of it is developed in-house, the infrastructure, yeah.
Is there classification, image classification or video classification?
Do you mean, do we process a single frame each time? Or do something which looks at a history?
Sequential classification or?
So the things that I've shown you so far are just information from a single frame. Okay, the old algorithms that I've shown you are things which are, there's multi-frame processing. So it's a system where you detect something in one frame, and then you have some modeling, filtering algorithm that gives you a coherent representation over time. So you effectively are using information from the past. Here, most of the things I'm showing you are actually information just from a single frame. And we are working on making things also, neural networks which do multi-frame processing.
This is from a single frame?
Yeah. Yeah. Yes?
Yeah, how do you differentiate between moving objects and a self or a scene moving, either the car? Like buildings.
Well, okay, in what context are you asking that question? I mean, why would we care if it's moving or not?
Because by that you can differentiate or detect pedestrians?
Okay, so actually, usually it's the other way around. We're good at detecting, for example, a pedestrian without knowing if it's moving or not, just by one image. So we have very strong classifiers, neural networks, which are able to tell you with very high precision that it's a human being. And then usually we'd go the other way around. We said, okay, if we know it's a human being, then we know this thing is going to move or may move. But I'll get to 3D reconstruction in a second. We're there. So, but okay, I'm not sure it will be a full answer, but we'll see. Well, ask me again if not. Okay, so so all this so far is really I've shown you things in the image, but as you know, people ask here, we eventually have to report the position of things in the environment in 3D. So we need to be able to say also not just that that's in the image where the vehicle is. We need to say what's the depth, where is it in the 3D world, and we're working on these things as well. Other car manufacturers usually do it by having two cameras and then doing stereo reconstruction. In Mobileye, we've always worked with one camera, and so life is hard, but it's interesting. So we're trying to reconstruct the 3D information with one camera, and I want to show you a little bit of things that we're doing there. So it's actually the way that you construct the 3D is by, or at least the way that we do it in others as well, is by looking at the motion in the image. Okay, as you drive, you see different parts of the image are moving to different locations, and there's depth information in there. Okay, so if you have these video games where you see stars that are going like that, you know you're moving forward, and you have a feeling for the distance of the stars, right? The ones that are moving faster are close, the ones that are moving slower are far. So we do a similar types of algorithms which track points in the image and see how they move. I'm doing like this because usually we drive forward and they move like that, but it's not necessarily. They also, if you rotate, they move left and right. And we try to reconstruct two things at the same time. One is the motion of the camera, and the other is the depth of the things that we see. Okay, there's two coupled problems. So I want to show you a little bit about how we results of estimation of the camera motion, and I've mentioned that we used that before. So yeah, so I have actually the video out there outside of the presentation, which I want to show you. Oh, sorry, it doesn't work with Media Player. We'll do it with VLC. Open with. Okay, so the camera motion is, we're talking about motion of a rigid body, and therefore it's 6 degrees of freedom. Okay, so we're trying to estimate between two consecutive frames what motion the camera did, which means translation in 3 dimensions, that's 3 numbers, and changes in 3 angles in 3 dimensions. These 3 more numbers, so total of 6 degrees of freedom. And the way we visualize it, so once you compute it, you have the problem of saying, well, whether this is good or not. So to visualize it, what we do is what I mentioned before. We integrate the future, so we're able to say what's the trajectory that the car has made at the future of this movie that I'm showing. And that's what you see drawn here. Are you able to see the lines here? They're fairly thin. There's a red line and a blue line. Do you see that there's lines at all? Oh, you see on the television, right. Okay. So the red line are the results of the algorithm. And by seeing that it goes along the road path, we know it's reasonable. But since we want to measure it more precisely, then we have a test car where we have an inertial navigation system which measures the vehicle motion, and the blue line is the same trajectory as measured by the navigation system. And as you can see, it's a fairly good match. And we're proud of this because the inertial navigation system is the way that you actually measure these things today. And it's a system that, if you want to get to these accuracies, costs $30,000. Our camera costs $100, and it's also using about 1% of its computational ability to compute that. So it's not that we're as good as the $30,000 system, but we're not much worse. You can see these small deviations. Okay, so that's one computation that's going on. I won't get too much into the math of that, but there's interesting math in there on how to actually infer from the motion of the points the 6 numbers of the motion of the car. And then once we do that, so suppose we know the motion of the camera because we solve that problem somehow, then it's easier to actually solve the depth problem. Because if you know that the camera moved in a certain way, you're able to predict a certain point in 3 dimensions where it's supposed to move to. If you don't know the depth, then you actually see where it moved to, and from that you infer the depth. You say if it moved by that amount, it means that was 15 meters deep. If it moved much less, it means that it's 50 meters deep, etc. Essentially, it's the same idea of the stereo, only instead of having 2 cameras this way, you have 2 cameras this way at different times. Okay? Question?
Yeah, does it work well on an empty, like an open road with only moving vehicles?
Okay, good point. So a limitation of that is that we can do that, or at least it's relatively doable if you do it on static objects. So for us, the moving objects are things that we're trying to get rid of and to try and reconstruct the static environment with that kind of method. Yeah, it's much harder to actually be able to say, well, these set of points are the bus, one rigid object moving. We didn't get to that yet. Yeah.
How sensitive are those algorithms to variations in the placement of the camera?
Okay, great. So with the stereo system, you calibrate it really precisely, the relative position of the 2 cameras, and then you're able to infer the depth in a fairly good way, if it's not too far, because they put the cameras in the cars about 10 centimeters apart, so up to 30, maybe 40 meters, you still can have a fairly good estimate of the depth. For us, as I said, it's a more complicated problem because each time you take 2 frames and you don't know the relative position of the 2 cameras, and you need this algorithm to actually infer that, and then after you use that, if it's accurate enough, you can infer the depth. But we're getting fairly good results. I can actually show you an image. So if you take that, let's go back to the presentation.
Why not add just another camera for the front?
When we work with car manufacturers, then you have very, very little flexibility on adding hardware. It's almost out of the question. So you give them the camera, and they want you to do as much as you can with that. And it might be that one of the main reasons that they actually chose you and not our competitors is because we said, well, we're going to do it with 1 camera. It's going to be easier for you. So that's one of our competitive edges that we said.
Use 8 cameras, you said. Well, that's only on the
So actually, even with the 8 cameras, there's fairly little overlap between the fields of view. So we won't have much of a stereo going on in there either. It will be just a bigger field of view, but not.
But then it's like 8 cameras versus 9 cameras. It's not a.
Yeah, it might be that at some point, we will switch back to. But so far, to our delight, we were able to match the competitions with our competitors and do the things with 1 camera, and we're trying to maintain that edge at least so far. Yeah.
You said something before about 6 degrees of freedom.
Yeah.
But actually, cars have, I think, 2 degrees of freedom, the wheel and going forward or backward. Maybe if you consider the bumper, it's the 3rd one.
Yeah.
So do you leverage this constraint?
it's something that actually my current job is actually related to the 3D reconstruction, so I can answer more about that. I did myself try to play with that idea recently, and because I thought the same thing, that car dynamics should constrain such that the 6 degrees of freedom are very correlated, that you could leverage that. I did some initial tests and was surprised to see that the car moves in ways that you might not expect. The correlations are much weaker than I hoped for, and so far we're not going there. Yeah?
For extracting the depth, do you need the self-speed of the car or not?
Oh, good. So we do need the self-speed of the car. There's actually, so I lied a little bit, because when we do this idea that you track points in the image and from that you reconstruct the 3D, we know everything up to scale, okay? Because you could imagine that the world could have been twice as large, the car could have moved twice as fast, everything would have looked the same. And so we need some external source of scale that would tell us, and the source of scale that we use is exactly what you just mentioned. It's the speed sensor of the car. The car, it's telling us we moved 2.1 meters, so we know that that's the distance between the cameras in the 2 frames.
And one more.
Yeah?
How can you be sure that this bus is not two cars, one truck, and in front of one bounding box instead of 2?
You're talking about the network that I've shown before that puts the bounding boxes on cars? Well, that's the machine learning did it for us. We showed it in enough examples where, not that it was easy, but it did it for us. Yeah.
You said that the 3D reconstruction is dependent on the speed of the car.
Yeah.
Then does it mean that when the car is stopped, say the traffic light, then it cannot identify depth?
Right. Yeah. It turns blind momentarily, but we maintain the 3D things that it remembers what it already saw, and it's waiting for it to start to move and then use. So we don't really do frame by frame, but we want to pass a certain distance between the 2 frames to actually get a substantial flow in the image. Yeah. Okay. How am I with time?
A little bit more than 2 minutes.
Oh, only 2 more minutes left? Or
13 minutes.
13 minutes? Okay, because I have 2 main topics. So maybe I'll leave the 3D reconstruction. I'll just show this as an example of how you can infer the depth if you know the motion of the camera. So the colors here are the different depths. But I think you understood the idea here, so I'll leave this topic and I'll move to the next topic. And I'm not sure I'll get to the last one. Okay. So far I talked about sensing, but it would be nice if the sensor has its limitations. It could be a very dark night or something like that. It would be nice if we also can rely on memory, at least for redundancy. And we said that if, for example, you want to know the lane structure, if you had a map which is accurate enough, and if you had localization which is accurate enough, you could use memory to know where to drive to. So how do we get that information? So there's a project that we've started to do with a number of car manufacturers. As an example, General Motors is one of our collaborators on this. And the idea is the following. So General Motors already has, or let's say next year, many cars, General Motors cars will come out in the US with our camera on it. So it means that you can crowdsource this problem. You can have these cars detect the lanes. Okay, so suppose this is one of the cars. It has our camera. It can detect the lanes. And then General Motors cars have a system that's called OnStar, which is connectivity with servers of the company, so it could upload the information that it found on where the lane marks are into the server. The server can build the map, And then a car that drives on that road can use that map. Now the question is, but how do you get actually the localization, right? Because we said that, so now we have actually a double localization problem. You have the localization problem of the car that's extracting the information, and then you have the localization problem of the car that we want to use that information, right? If they can't locate themselves on the map accurately enough, it's useless. So the system that we came up with is we leverage the image detection abilities that we have to detect the different signs and markings on the road that you can find. And then at each point, we know more or less where we are with the GPS, but now we get a very, very refined positioning by triangulating the different signs that we see. We get an exact position. And we use the same system also for the car that's going to use that information, because it would be able to recognize these same landmarks. Okay, we upload the landmarks as well, not just the lane information, but the landmarks. And then the car that's going to use it is going to locate itself also with these landmarks, going to use the lane information, and it will be able to drive by memory. Okay, that's the basic idea. There's also one of the interesting things about it was that we needed to do it with a very narrow bandwidth. So GM system the limitation that they gave us is for every kilometer you can send 10K of information. And other systems that have been built for HD maps, it's called high definition maps, usually talk about gigabytes per kilometer. So here we really came up with a way where the information is very compact. You just have a very compact representation of the lanes that you can drive in. You have a compact representation of these landmarks. We don't send images or any raw data, but we do a lot of onboard processing to get this into this compact representation, and that's what we send to the server. Okay, so that's another project that we're working on. Actually, I have a demo of that. Yeah.
So I could understand how you overlay the images of the two cars quite accurately, but I don't understand how you position the static objects accurately.
So the static objects, okay, so this is a point I skipped here. When you drive past a sign and you see it multiple times, you're actually able to triangulate that and get a 3D position of that landmark, of that sign. If you do it for multiple signs, you get both the 3D position of those signs and your relative motion relative to these landmarks. Okay? Does that answer the question? Okay. Just to show a small demo. So this is a nice junction in Jerusalem. These are the lanes that have been pre-mapped by the system. And now the car is using that map. This is the position where it locates itself. And as we drive, you see here in green the different landmarks that it recognizes to locate itself. And you see here in yellow the lane that it thinks that it should drive along based on the memory. Okay. And if there's no questions about that, yeah.
I don't understand if those landmarks that it identifies are correspondent to the landmarks downloaded from the cloud in a way, or are those just landmarks that the car itself identified and stored?
No, it is uploaded to the, so when we drive, we know roughly what area we are at, and the car that's extracting information says, I see that particular type of sign, okay, let's say this type of arrow on the road, and it gives it a signature, and it sends it up to the cloud. So now it's part of the map, and it will be used, this particular arrow would be used when other cars come and drive and need to locate themselves in there.
It uploads the signature, but it also downloads the signature.
Yes, right.
To localize itself.
Yes, right. And of course you need to match what you see.
Your relative positioning, right? Not an absolute position.
Okay, so there's an interesting point there, which is when we started, we were interested, because we're interested in autonomous driving, we didn't really care if we are, globally our map is correct. Only we cared only that, with the next 100 meters, the structure of the lane would be accurate enough to drive. But we find, as we work with car companies increasingly, that for them it's really hard to think that way, and they want it to be exact in the global system. So we are starting to do steps to make it exact in the global coordinate system. Okay.